In today's episode, we're talking about amine stress corrosion cracking, what it is, where it happens, and how to stop it. Amine stress corrosion cracking is a persistent and costly challenge for operators. This form of corrosion can compromise critical equipment and facilities, potentially leading to unplanned shutdowns, environmental incidents, and significant financial losses. Understanding the mechanisms behind ASCC is the first step for facility operators and reliability engineers toward implementing effective prevention strategies. The combination of corrosive amine environments, fluctuating temperatures, and mechanical stresses creates an ideal environment for this damage mechanism to develop, often in the most critical components of an amine regeneration unit. This comprehensive guide explores the causes, effects, and most importantly, the solutions to amine stress corrosion cracking. Drawing on decades of industry experience and research, we'll examine how modern protection technologies are revolutionizing amine corrosion management and extending the operational life of these mission-critical assets. Amine stress corrosion cracking is a form of alkaline stress corrosion cracking, specifically targeting carbon and low alloy steels in lean amine environments. It's important to note that this is distinct from the cracking in rich amine systems, which is actually a form of wet H2S cracking, also known as sulfide stress cracking. ASCC is common in amine regeneration units where the combination of corrosive chemicals, high temperatures, and mechanical stress creates ideal conditions for this type of corrosion. ASCC primarily affects facilities in oil and gas production, refineries, natural gas processing, petrochemical manufacturing, and carbon capture systems. The amine regeneration process is fundamental to gas sweetening operations, removing acid gases like H2S and CO2 from hydrocarbon streams. This critical process involves several key components: the amine absorber or contactor, where sour gas contacts the amine solution; the amine flash tank, where hydrocarbon vapors are removed; the amine regenerator column, where acid gases are stripped from the rich amine; and the amine reboiler, where heat is applied to facilitate regeneration. According to industry data, almost 50% of corrosion in amine systems occurs in the hottest parts of the plant, the amine reboiler and the bottom of the amine regenerator column. This is mainly because corrosion rates accelerate at higher temperatures, with acid gas breakout creating highly corrosive conditions. Amine unit corrosion in refineries occurs through several interrelated mechanisms that can be categorized into chemical, operational, and metallurgical factors. Chemically, amine type and concentration play a significant role in corrosion susceptibility, as different amines, AMEA, DEA, MD, EA, DGA, exhibit varying corrosivity profiles. A comprehensive NACE survey of 294 amine units found 164 reported stress corrosion cracking cases in MEA systems compared to just 37 in DEA and 30 in other amines like ADIP. The study revealed that cracking was predominantly intergranular and oxide-filled, occurring most frequently in weld heat-affected zones. H2S and CO2 concentrations directly impact corrosion potential, and the formation of heat-stable salts reduces the amine's effectiveness while increasing its corrosivity. Oxygen ingress can dramatically accelerate corrosion, and solution pH significantly influences corrosion rates and cracking susceptibility. Operationally, elevated temperatures in the amine regeneration unit accelerate corrosion reactions exponentially. Pressure fluctuations create stress cycles that can initiate and propagate cracks. Two-phase flow conditions cause erosion corrosion due to droplet impingement, and flashing conditions lead to localized attack and pitting. Velocity effects are also critical, as high velocity areas experience flow-enhanced corrosion. Metallurgically, the underlying material composition determines corrosion resistance. Residual stresses from fabrication, welding, or cold working create sites for crack initiation. Microstructural features like grain boundaries and inclusions can serve as initiation points. Improper heat treatment can lead to increased susceptibility to ASCC. Not all materials respond equally to amine environments. Carbon steel, while cost-effective and commonly used, is susceptible to general corrosion, pitting, and ASCC, particularly in hot, regenerated amine service. Austenitic stainless steels offer improved resistance, but can still suffer from chloride-induced stress corrosion cracking at weld heat-affected zones. High alloy materials like Inconel and Hastelloy provide excellent resistance, but are significantly more expensive, making them suitable only for critical components. There are effective amine corrosion management methods available that require a multifaceted approach. In terms of material selection, operators should use appropriate corrosion allowances, consider composite construction with CRE cladding, specify post-weld heat treatment, and implement proper weld procedures. For process control, it is important to maintain recommended amine concentration and loading limits, control solution temperature, implement effective filtration, regularly analyze and maintain amine chemistry, and monitor oxygen ingress. Modern corrosion prevention strategies include innovative approaches like high-velocity thermal spray cladding systems. Unlike traditional methods, HVTS offers several advantages: application without heat-affected zones, faster application than welding, compatibility with existing weld overlays, superior corrosion and erosion resistance, no need for post-weld heat treatment, superior mechanical properties compared to organic coatings, wide service temperature and pressure ranges, in situ application during scheduled turnarounds, and long-term protection against sweet corrosion and sour gas attack. HVTS technology has become increasingly recognized as a standard practice for protecting amine systems across the oil and gas industry. Major energy companies, including Phillips 66, Shell, ExxonMobil, Chevron, and BP, have adopted this technology as their preferred solution. The widespread implementation of HVTS in facilities across North America, Europe, and the Middle East demonstrates its effectiveness and reliability. During a scheduled turnaround inspection, a Phillips 66 gas treating facility in Giddings, Texas, discovered severe corrosion damage in the main amine regenerator column between trace 13 and 18, directly attributed to aggressive amine attack on the carbon steel shell. The facility had historically relied on periodic weld buildup and organic coatings, which proved ineffective and costly. After evaluating several options, Phillips 66 selected IGS HVTS technology. The application covered 277 square feet and was completed in 5 shifts without creating heat-affected zones or requiring post-weld heat treatment. This significantly reduced downtime. By implementing HVTS, Phillips 66 eliminated the need for recurring repairs, reduced total asset ownership costs, created a permanent corrosion barrier, and minimized future maintenance requirements. The facility plans to verify the cladding's performance during its next scheduled inspection in 5 years. Beyond Phillips 66, other facilities have successfully adopted HVTS technology. Shell has standardized HVTS in their amine units. ExxonMobil uses it in MDEA units. Chevron has implemented it in refinery and gas processing units, and several Middle Eastern national oil companies have made it their standard for new builds and retrofit. European refiners are also turning to HVTS as a permanent solution, reporting substantial improvements in reliability and reduced maintenance. Amine stress corrosion cracking is a significant challenge in oil and gas processing. Operators can effectively manage this issue by understanding the mechanisms, selecting the right materials, and applying advanced protection systems like HVTS cladding. A proactive approach to corrosion control ensures reliable operation, extends asset life, and avoids the high costs associated with corrosion failures. And that's it for today's episode of the Efficiency and Reliability Podcast.